Welcome back, children. Today's topic is magnetism and matter. In the last chapter, we discussed magnetism from moving charges as well as current carrying wires. The source of magnetic field is known to be current. That may be moving charges, that may be drift of electrons in a conductor in the presence of electric field inside it, or it can be due to orbital motion of electron in atoms. All that arises from currents only. Magnetic fields generally arise from current. Okay, here we learn about permanent magnetic field. Permanent magnetic field also arises from current orbital motion of electron in atoms of the substances. A bar magnet is a very popular permanent magnet which is used in laboratories. Bar magnet also appears in dipoles, two poles, north pole and south pole. Every magnetic configurations need not have a north pole and south pole, but magnetism is seen in closed loops of field lines. For a permanent magnet, say bar magnet, magnetic fields appear to be originated from north, appear to be terminated at south, but it forms closed loops, continuous closed loops from south to north internally. So when you draw the picture of a permanent magnet, maybe this one, which has a south and north pole, the magnetic poles are slightly found to be inside the geographic ends. So the geographic length is slightly more than the magnetic length. Magnetic length is the distance between two magnetic poles, and the strength of each of these magnetic poles called pole strength. Pole strength sometimes called magnetic charge assigned to each of these poles. Pole strength of each poles are same. Now, if L is the or 2L is the effective length of the magnet, then magnetic dipole moment M is defined as the product of pole strength as well as the magnetic length. Direction of magnetic dipole moment is from south to north, which is same as the direction of this magnetic length. Moment is a vector. Unit is ampere meter square. That is why pole strength has unit ampere meter. Moment has unit ampere meter into meter, ampere meter square. So pole strength ampere meter, moment ampere meter square. Students, pole strength sometimes called magnetic charge assigned to poles, that is used in NCERT text. And the magnetic field lines appear to be originating from north and appear to be terminating at south, but it makes continuous closed loops from south to north. So here magnetic field forms continuous closed loops. The magnetic field is not completely confined or not parallel to one another outside this bar magnet. So this is the formula for moment of the bar magnet, pole strength into 2L. So this topic is very important. This can be compared with a solenoid. Also this can be compared with a current loop. You can have a current loop like this, which carries a current whose axis can be shown like this. You know, current loop is also a magnetic dipole. For getting a south polarity to the left, you should have an anti-clockwise current as looking from left side. Sorry, clockwise current when you looking from left side. As you look from this side where I am standing, you will see a clockwise current where the polarity is south, the other side it is going to be northward. The direction of moment of this current loop is equal to NIA. So current loop has a magnetic moment, permanent magnet also has a magnetic moment. You can compare the moments of each. Current loop is a magnetic dipole. This is also a magnetic dipole. What is Gauss's law? Gauss's law states that closed integral E dot ds is equal to Q enclosed divided by epsilon naught. Here in magnetism, if you try to find out a similar law, you'll write closed integral B dot ds equal to, normally we should write 1 by epsilon 0 replaced by mu 0. When you transit from electricity to magnetism, the constant 1 by epsilon 0 should be replaced with the mu 0. That also may be asked in exam. Times charge enclosed should be replaced by this magnetic charge or pole strength. So I am writing magnetic charge enclosed. Okay, this is the expected one. But what happens is that in magnetism there are no monopoles. That is why the right hand side written should be incorrect. As there is no net pole strength, as there is no net magnetic charge for each magnetic configuration, therefore the right hand side should be 0. What do you mean by that? Left hand side says that the total magnetic flux, that is total magnetic flux through any closed surface, that is going to be 0. That is Gauss's law in magnetism, which is the clear evidence of no magnetic monopoles. So magnetism, there are only dipoles, no monopoles. But in electricity, there can be monopoles as well as dipoles. In electricity, there can be monopoles as well as dipoles. That's Gauss's law in magnetism states that the total magnetic flux through any closed surface is equal to 0, which tells you that there is no magnetic monopole. In magnetism, only dipoles are present. Okay, that's very important thing. Now, what's the field due to a permanent magnet? That is to be revised from this chapter. That's very important. You have a bar magnet like this, whose moment is directed from south to north. If you try to find field at a point P, which is at a distance r from center of the dipole, which can be compared with electrostatics, and we can say that field, magnetic field induction, flux density at the point P is given by magnetic constant mu naught by 4 pi, mu 0 by 4 pi. Then what's the formula for current loop magnetic dipole? Current loop is a magnetic dipole. There we have learned that mu 0 by 4 pi 2m divided by r cube, where m stands for magnetic dipole moment for a short bar magnet. So we have only short magnets in syllabus. For a short magnet, mu 0 by 4 pi 2m by r cube, and direction of the magnetic field is same as the direction of moment. So field along axis is equal to, field along axis is along moment. Field along axis is equal to moment. But along bisector, at any point you choose, field along bisector is found to be in opposite direction of the moment. So field along bisector, that is equal to minus mu naught by 4 pi as in electricity, m divided by r cube, that is exactly half that at same distance. If this distance is same, the field is reduced by a factor of 1 by 2 at same distances along axis. If the field is B0, along bisector, the same field is B0 by 2. Field along axis B0, field along bisector B0 by 2. Also, care should be taken, the direction of magnetic field along the bisector line is opposite to the moment along axis. Field along moment along bisector, all along bisector, at any point along bisector. Field due to that short magnet is directed opposite to its moment. That's very important concept. Okay, so magnetic field along the axis as well as along the bisector. Now, when this magnet is kept in external uniform magnetic field, we have this bar magnet or any magnetic dipole when kept in external uniform magnetic field, we have learned that that has a torque, that experiences a torque. If you keep it like this experiences a torque. This is the direction of the magnetic dipole moment. magnetic dipole moment directed from south to north, m vector, and angle theta with the external magnetic field. We have already discussed in last chapter that tau is equal to m cross b. There we use the current loop, here we use a permanent magnet. That's all. Same result. So torque is equal to m cross b, torque is equal to mb sine theta. That is why at this configuration it has a potential energy given by minus m dot b. That can be written as minus mb cos theta. Potential energy minimum is given by minus mb. That is when theta is equal to 0. When theta equal to 0, that dipole happens to be in stable equilibrium where it possesses minimum potential energy, but at theta equal to 180 degree, potential energy happens to be maximum, which is plus mb, which is called unstable equilibrium. So what is the minimum work done by an external agency in turning this dipole from stable equilibrium to unstable equilibrium? Let me show that how it happens here. See, suppose this is the magnet and whose axis is along the field. Now, the magnet is to be turned through 180 degree like this. What is the work done? Minimum work required to turn it from, see, stable equilibrium to unstable equilibrium. What is that minimum work done? That is mb is the potential energy when it is theta equal to 180, minus mb is that when theta equal to 0. So final minus initial, plus mb minus mb, that happens to be 2 mb. So maximum work done is in reversing this, which is nothing but 2 mb. But from any angle theta, if you turn like this, it is there. It is now like this. Now you turn it from here to such a position, then you need not use this equation 2mb, but you use 2mb cos theta. So from this configuration, when you turn through 180 degree current position, 180 degree, then that is 2mb cos theta. From stable to unstable, it is 2mb only. So maximum work is needed to be turned from stable to unstable. This topic is very important. Now, this magnet you slightly disturb and leave, it will execute simple harmonic oscillations. For small oscillations, the time period can be measured as 2 pi root I divided by mb. So t proportional to square root of I, where I stands for moment of inertia. T proportional to 1 by square root of magnetic dipole moment of the magnet. When you cut a magnet into two pieces along the transverse bisector, what happens to the magnetic dipole moment? All that very important. If you cut along the transverse bisector, you get two pieces. Okay. You cut it. You get two pieces like this. Now, the moment of the first piece, uncut piece is m, that moment of the cut half piece is m by 2, this also m by 2. On cutting like this, pole strength does not change, same pole strength, but length halved, that's why moment halved. Okay, so when cutting a bar magnet into two equal pieces along the transverse bisector, each pieces will have moment m by 2 because length halved without any change in moment. Now t proportional 1 by root n, that type of questions may be asked. Other one, t proportional to 1 by square root of b, where b is the external magnetic field. On doubling the external field, period becomes 1 by root 2 times. On quadrupling the magnetic field, period becomes half. Similarly, you try to find out the formula for the frequency. Frequency is reciprocal of time period, which is nothing but 1 by 2 pi root mb divided by I. So frequency proportional to square root of moment. If you double moment, that means you cannot double the moment of a given magnet. Already undergone a saturation magnetization, but you take another magnet of double the moment, you can say that the frequency becomes root 2 times. That type of questions are also important. And this formula is based on an experiment done in the laboratory. And that experiment based on an apparatus called vibration magnetometer. So this is the formula for time period of small oscillations of a magnetic dipole oscillating in vibration magnetometer. Okay, vibration magnetometer can be used for finding moment of a magnet M. From this you can use the formula moment M is equal to what? Moment M is 4 pi square I divided by B T square. For pi square, uh, I divided by Bt square, formula for moment. This can also be used for finding magnetic flux density at any point. May be used for finding horizontal component of Earth's field. In this vibration magnetometer, there is a suspension stirrup where only this bar magnet is suspended horizontally in equilibrium. That will be showing the direction of magnetic poles north and south. So that suspended magnet in the vibration magnetometer device happens to be orienting in the magnetic meridian of Earth. Disturb that orientation slightly by using another magnet from outside the device without touching it. Then you can produce a small deflection there, due to which it can start oscillating. For small oscillations, that is simple harmonic with restoring torque mb sin theta, potential energy changing on the basis of minus mb cos theta. All that questions may come with period 2 pi root I by mb. Okay, there you can find out the horizontal component of Earth's field by finding out the number of oscillations taken by the magnet for 20 oscillations or so. Finding out the time period, doing the experiment repeatedly, you can find out the external field B, which is the horizontal component of Earth's field, because as the magnet is suspended horizontally in a stirrup, aluminum stirrup, then it oscillates periodically, simple harmonically, horizontally in the horizontal field of Earth. So you can find out the horizontal component of Earth's field. So these type of questions are very popular and important there. Now, terrestrial magnetism is the next topic to be revised. Magnetism of Earth. Earth is assumed to be a uniform sphere. Earlier, it was believed that there is a huge magnet buried at the center of Earth, whose length is equal to the diameter of Earth, but it was meaningless because Earth contains molten ferromagnetic core. So no solid state substances can be there at the inner core. That's why that was incorrect. New theories say that as per dynamo effect, the ferromagnetic deposits, fluids, iron, cobalt, nickel, etc., as the core of the fast rotating planet produces a current loop inside, because all these ferromagnetic materials have large number of free electrons. These electrons form domains. This domains formation give rise to permanent magnetic dipole moment of that huge planet as it is fast rotating. Then that produces magnetic dipole moment permanently. That's why the planet has got a magnetic field. Moon has a feeble or no magnetic field because Moon has no hot core. Jupiter has fastest rate of rotation, that's why it has strong magnetic field. Earth also has rate of rotation and hot core, that's why as per dynamo effect, magnetic field is present. Okay, this is the direction of north geographic, and this may be north magnetic. North geographic and north magnetic are not found at same point. It is very close to 500 miles or 800 kilometers apart from one another. Really, these two axes coincide at the center of Earth. Okay, this happens, and this angle presently is found to be 11.3 degree approximately, and it found to be varying. True north and south does not vary. True north, true south means N geographic, N south. N geographic north and geographic south. Okay, sorry, we have to write south geographic. And here north magnetic and this is south magnetic. Earth has a magnetic field directed from south magnetic pole on to north magnetic pole. So magnetic field of Earth is directed from south magnetic pole of Earth to north magnetic pole of Earth. Before that, let us define what is magnetic south pole of Earth. Magnetic south pole of Earth is defined as the pole towards which south pole of a freely suspended magnet points. Then, what is the north magnetic pole of Earth? North magnetic pole of Earth is defined as the pole towards which north pole of a freely suspended magnet points. Okay. As per that Cartesian convention only, we adopt this rule that direction of Earth's magnetic field is directed from magnetic south pole of Earth to magnetic north pole of Earth. Always the field is from bottom to top, only like this externally, and internally that field makes continuous closed loops. That's the direction of the moment also. Moment is now directed from magnetic north pole to magnetic south pole inside. That's the direction. But normally magnetic dipole moment of a magnet is directed from south to north. We have learned. Here along the axis field should be in the same direction of that of moment. Okay, is it clear? This is the reason. Dynamo effect is explained to be the reason why the planet has a magnetic field. Hope that it is clear. Now, going to magnetic elements of Earth. There are minimum 3 parameters, measuring parameters required for geographic mapping and all. For locating a particular place on surface of Earth magnetically as geographically, we need certain elements. That minimum required elements are called elements of Earth's magnetic field. The first one is called magnetic declination. Magnetic declination. What do you mean by magnetic declination? Magnetic declination at a place on surface of Earth is the horizontal angle between geographic meridian and magnetic meridian at the given place. So what is magnetic declination? Magnetic declination is the horizontal angle defined at a place on surface of Earth made between magnetic meridian and geographic meridian at the same place. Okay, at different locations on surface of Earth due to this spherical shape and unequal positions of geographic pole and magnetic pole, the magnetic meridian and geographic meridian will not be identical. Some places, geographic meridian will not make any angle with the magnetic meridian from surface of Earth. Those places are like this, that if you look towards geographic meridian, geographic pole from some particular point on surface of Earth, you can see the magnetic pole just behind it without any parallax. Without any parallactic angle, if you are watching these two together, suppose you are standing close to Parliament, Indian Parliament, New Delhi, and you can watch India Gate behind it. Actually, 2 or 3 kilometers apart, these two, but you can see without any parallax. Like that, you are seeing this 500 miles separated geographic North Pole and magnetic North Pole together without parallax. Then we can say that there is no declination. Like that, no declination. So there are several points on surface of Earth with 0 declination. Declination changes from place to place over surface of Earth. Okay, that is magnetic declination. Magnetic declination. Device used for measuring declination is called Q magnetometer. Magnetic declination. Magnetic declination has got a Cartesian convention that if at a place on surface of Earth, if magnetic North Pole is found to be to the east of geographic North Pole, that is called positive declination or easterly declination. Here I have shown a positive declination. When positive declination? When magnetic North Pole is located to the eastern side of, to the rightward side of true north or geographic north, then that is positive. Otherwise, it is negative. At a given place when you are looking towards without any parallax, if both the poles are seemingly in same line, then there is no declination. So three possibilities: no declination, positive declination, and negative declination. The second one is magnetic inclination. Magnetic inclination. Magnetic inclination is also called magnetic dip. Inclination or dip. As the name tells, when a bar magnet is suspended, uniform bar magnet is suspended about its center of gravity, depending upon the location of the place where you are suspending it about center of gravity, it won't be horizontal. It is perfectly horizontal exactly at magnetic equator. But if you move from magnetic equator to either of the poles, magnetic poles, north or south pole, the corresponding poles descend. Northern hemisphere, north pole descends. Southern hemisphere, south pole descends. So when a magnet is freely suspended, surely it will be suspended in magnetic meridian. When it is in magnetic meridian, the angle to which it descends or ascends, northern hemisphere, north pole ascends and south pole, north pole descends and south pole ascends. Southern hemisphere, south pole descends and north pole ascends. Angle through which either of this pole ascends or descends with horizontal is called magnetic inclination or dip or true dip. True dip is measured when the magnet is suspended freely. That means when it is in magnetic meridian. Okay. So when a bar magnet is suspended, it is found to be tilted a little with the horizontal. That is called true dip. When that is done in the magnetic meridian. Magnetic meridian is the vertical plane passing through magnetic axis of Earth. Okay. Then here, resultant field would be this hypotenuse, and that is the direction of that inclination. So magnet inclined along the resultant field, you can resolve into rectangular components BH and BV, so that you can find out tan theta is equal to BV by BH, sin theta equal to BV divided by B, cos theta equal to BH by B, all that. Then modulus of the resultant magnetic field is given by root of BH square plus BV square. Tan theta equal to BV divided by BH. If theta is 45, tan 45 is 1, so that BV by BH is equal to 1, then BV is equal to BH. If BV equal to root 3 times BH, theta happens to be 60. All that true dip, right? But when you suspend that bar magnet using a torsionless string and turn it from magnetic meridian, you turn that string, what happens? By forcefully you are turning that, twisting, you produce little twist, then that magnet automatically turns gradually and gradually it turns. Then you can see that the inclination or the dip angle changing, and that is always increasing. The true dip is measured in meridian, but you tilt that magnet horizontally through some angle phi, say that angle is phi, true dip is theta, then through a horizontal angle phi, when that magnet is tilted, you will notice that that new dip is the new observed dip is greater than the true dip, and that observed dip is called apparent dip. The formula for apparent dip is very important. Formula for apparent dip. Apparent dip, tan theta dash is equal to tan theta divided by cos phi. Tan theta dash equal to tan theta by cos phi. That means if you tilt that magnet horizontally from magnetic meridian through an angle 90 degree, you can find that tan theta dash is equal to tan theta divided by cos 90. Cos 90 value becomes 0. So tan theta by 0, it becomes infinity. Infinity means not defined, for which theta dash also should be 90. Theta dash is the apparent dip, virtual dip or false dip, observed dip, recorded dip, whatever. Maybe in question papers. So when a bar magnet is suspended in magnetic meridian, the dip is true dip. You turn it by some way, allowing it to freely turn vertically. You are turning horizontally, but it is free to rotate vertically, free to move vertically. Now that new angle through which that magnet tilts is greater than the original angle, initial angle. That new angle is called observed dip or apparent dip, given by tan theta by cos phi. Theta true dip, theta dash apparent dip, phi horizontal angle. If that horizontal angle is 90 degree, that means you are turning that magnet through 90 degree with the meridian, then that dip is said to be 90 degree. That is why a magnetic dipole, when turned through 90 degree with magnetic meridian, remains vertical. So when in magnetic meridian, it may be having only this much of tilt. You turn around through 90 degree, then it will stay vertical because the apparent dip is 90 degree. That's dip. Device measuring dip is dip needle or dip circle. Dip needle or dip circle. The third one is horizontal component of Earth's magnetic field. Horizontal component of Earth's magnetic field direction can be found using compass needle. So compass needle shows the direction of horizontal component. Dip needle shows the direction of resultant magnetic field. And magnetic declination shows the horizontal angle between true north and magnetic north at that given place. Okay, these are the three magnetic elements. Now we have to revise the next topic, that is different types of magnetic materials. First one is a ferromagnetic material. Ferromagnetic materials are those materials which have strong magnetization. Strong magnetization. So mu r is much larger. Much larger than 1. That means mu r may be few hundreds. Permeability is large. Relative permeability is a number mu r, round figure number, that is close to 100, 150, 250, 200, like that. Okay, ferromagnetic materials will have greater values of susceptibility also. Magnetic susceptibility. Susceptibility of a ferromagnetic material can be defined as B minus B0 by B0. What is this? What is the meaning of this? You have a solenoid. A solenoid. When there is no core, then the field strength is B0. But you insert a soft iron core, the field strength, flux density or magnetic induction increases by a percentage. What is that percentage increase? What is the fractional increase in the magnetic field strength? B minus B0 by B0, where B is the new field. B0 can be written as mu 0 Ni. B can be written as mu 0 mu r Ni. Okay, B is mu 0 mu r Ni, B0 is mu 0 Ni. So field B is much greater than B0 for a ferromagnetic material. That is why that fractional increase in the magnetic flux density of that solenoid in the presence of the soft iron core, that fractional rise is called susceptibility. Okay, now ferromagnetic materials are highly susceptible. That is why susceptibility is larger. That percentage increase in the magnetic flux density is called susceptibility. In 2022 mains paper, this question was asked. And this value B minus B0 by B0 value was given. And what is susceptibility? That was the question. That question was the same as the answer, both sides. So susceptibility, magnetic susceptibility. This formula is important. Also, chi can be measured as the ratio of magnetization vector M and H. H is magnetic intensity. when you pass a current I through this, the external magnetizing field H is equal to Ni. H is called the external magnetizing field. H does not depend on the core. H is equal to Ni. That's another one. B equal to mu 0 Ni. That is why B0 equal to mu 0 H. So that H can be also measured as B0 divided by mu 0. H does not depend on the core. That is important. That is from NCERT solved exercise. It is mentioned. So it's important. Chi equal to M by H. So M can be written as chi H. Susceptibility may be given. H may be given. You can find out the magnetization M. Magnetization M is equal to B minus B0 by B0 into H. All this formula to be noted. Okay. Also, susceptibility chi as per Curie-Weiss law. Curie-Weiss law, susceptibility is measured as C by T minus Tc, where C is Curie's constant, proportionality constant, and Tc is a critical temperature, a transition temperature, Curie temperature, above which a ferromagnetic material becomes paramagnetic. And this Curie-Weiss law only valid when T greater than Tc, for which susceptibility should be positive. For ferromagnetic materials, susceptibility is a positive large figure. Susceptibility is a large positive. Relative permeability is equal to 100. Then susceptibility equal to 99. Relationship is mu R is equal to 1 plus chi. This formula is also to be revised well. So chi equal to C by T minus Tc only applicable when T greater than Tc. When T greater than Tc, that material goes to paramagnetic state. The ferromagnetic material goes to paramagnetic state. That means it shows paramagnetic properties when temperature is increased and it has value greater than the Curie temperature. Curie temperature is different for different substances. This law is called Curie-Weiss law. So this type of formula very important. Susceptibility, magnetic intensity. Next page I will continue. So once again, H is equal to Ni. One more equation for vector equation for this H, which is measured as B by mu 0 minus M, where magnetization M is defined as the total magnetic dipole moment vector divided by volume. That is called magnetization. Magnetization is the total magnetic dipole moment by volume. If you go for a graph between magnetization and H, H is plotted on horizontal axis and magnetization is plotted on vertical axis. You get, as a previous question, you get a graph, first increases, then becomes maximum and a constant. That means M by H first increases, then becomes a constant. So magnetization vector has a property of saturation. This happens when all the domains of that ferromagnetic materials aligned in the same direction of the external magnetic field. Again, revising what is a domain. Domains formation is an important feature of ferromagnetic materials. Domains are of small size to very small volumes, maybe of 1 micrometer size, maybe cubes of 1 micrometer side, containing huge number of atoms, for example 10 to the power 11 atoms. And each of the domains will have a unique moment. But when unmagnetized, total dipole moment of all the domains would be 0. Each of the moments, each of the domains will have their own characteristic moment. But when unmagnetized, due to random orientations, the resultant dipole moment of all the domains is 0. But in the presence of external magnetizing field, all the domains align, and that gives rise to resultant magnetic field. That is why there is a large and positive magnetization for all ferromagnetic materials. When temperature increases, susceptibility of ferromagnetic material decreases, and it goes to paramagnetic phase at a temperature above called Curie temperature. Okay, below Curie temperature only sorry, above Curie temperature only, that Curie V law is accepted. Chi equal to C by T minus Tc. That is called Curie V law. That's very important one. These all topics are to be noted. Now, paramagnetic materials are having feeble magnetization properties, but still they will attract. Ferromagnetism means strong attraction, paramagnetism means feeble attraction. Paramagnetic materials are those materials which can be attracted but feebly in magnetic fields. Ferromagnetic materials are strongly attracted, but paramagnetic materials are only feebly attracted in external magnetic field. Okay. Paramagnetic materials are those materials whose atoms having permanent dipole moment, but only moment very feeble. In the presence of external magnetic field, that domain formation are not happening. But each of these magnetic dipoles will align only feebly. That's why the resultant magnetization seen is so feeble. Not as in ferromagnetic materials. In ferromagnetic materials, the resultant field is strong. Magnetization is large and positive. Paramagnetic materials also, when you increase the temperature, susceptibility found to be decreasing. Susceptibility of a paramagnetic material. Paramagnetic. Susceptibility found to be varying inversely proportional to the temperature. That's very important. Susceptibility can be measured as C mu 0 by T. Chi can be written as M by H. Mu 0 can be written as B0 divided by H. H cancels, so M equal to C B0 by T. This is also a very important formula. Okay, this may be asked in entrance. M B0 T values may be given. So one sets of values will be given, and the other set you can find out M1 equal to B0 1 by T1, M2 equal to C B0 2 by T2. Like that you can compare. Comparison questions may be coming. Chi T graph is a rectangular hyperbola, so that Chi1 by Chi2 equals T2 by T1. These are the important equations of this chapter, and this law is called Curie's law. Curie's law. Earlier one was Curie-V's law. This is Curie's law. Susceptibility varies inversely with the temperature. Temperature should be measured in Kelvin scale. Temperature may be given in degrees Celsius, convert into Kelvin. Next one is diamagnetism. Diamagnetic materials are those materials whose atoms do not have permanent dipole moment. But in the presence of external magnetizing field, each of that dipoles will gain magnetic dipole moments called induced dipole moments, but that is against the applied field. That's why it results in negative susceptibility. Susceptibility negative. Relative permeability is very less. Relative permeability of diamagnetic materials lies between, that is less than 1 and greater than 0. For example, relative permeability value may be 0.5 is as an example. Susceptibility is negative. The value will lie between. Chi is less than 0 but greater than -1. Susceptibility lies between 0 and -1 for diamagnetic materials. Don't forget this one. These two asked in examinations. So susceptibility, negative susceptibility or reverse magnetization. Reverse or negative magnetization. These are the features. Also diamagnetic materials, susceptibility does not depend on temperature. Susceptibility temperature graph, if you plot like this, you get a straight line parallel to temperature axis. Susceptibility of diamagnetic materials does not depend on temperature. Now examples also. Diamagnetic materials, lots of examples. Gold, diamond, water, copper, many examples. Okay, alcohol, silicon. Okay, all these are examples of diamagnetic materials. Ferromagnetic materials already we have discussed, iron, cobalt, nickel. Then paramagnetic materials, sodium, potassium, calcium, aluminum, all these paramagnetic materials. So collect maximum examples from textbook. Okay, that may be asked. So ferro, para and dia. Now, Permanent and temporary magnets. This is very important, and many question paper we used to see these questions. Permanent magnets are those magnets which are permanently magnets. Permanent magnets, we have to choose materials with a high permeability. Permanent magnets materials should be of high permeability, high retentivity, high permeability, high saturation magnetic field. All these phenomena, high permeability, high retentivity, then high coercivity. What do you mean by coercivity? Coercive field is the reverse field required to demagnetize it permanently. A permanent magnet should not erase its magnetism easily, should not. It should be permanently magnet. So it should not be easily demotivated, demagnetized, should not be easily demagnetized. Some of you may be easily demotivated. Should not be. That's high coercive. High coercivity means that you cannot get disappointed when your result is so poor. Okay, like when the field is removed, it is very easy to remove the field from a material, then coercivity is less. Permanent magnet should have large coercivity, large retentivity, large magnetic field, all large. But a temporary magnet should be only temporary magnet. Electromagnets are temporary magnets. A solenoid, when only current passes, it behaves as a magnet. When current is withdrawn, it should not be. That is why the coercivity should be less, retentivity should be less, but permeability should be greater. For temporary magnet, coercivity and retentivity should be as small as possible. Okay, that's the thing. We need to have high permeability, high retentivity, high coercivity for permanent magnet. Then high permeability, low retentivity, low coercivity for temporary magnets. We used to have a BH graph plotted for every ferromagnetic materials. You try to find out the BH graph. How that graph is plotted, it's very popular graph, and H is plotted along horizontal axis, B along vertical axis, B measured in Tesla, H measured in ampere per meter, unit of H and M. Magnetization and magnetic intensity vector both are having same dimensions, ampere per meter. Flux density field B in Tesla. You used to get a graph of this type. This closed loop formed is called hysteresis loop, may be named O, A, B, C, D, E, F. Arrow marks can be shown like this. When magnetized, a ferromagnetic material taking inside a solenoid by increasing the current, H is equal to Ni. Then H increases. When H increases, B increases. Okay. Quickly, but later on, when H increases, B does not increase considerably, but B is not saturated. That's why it will not go parallel. It will slightly go steeper, but steepness will be less. Then you stop increasing the current, you try to decrease the current, then H decreases. But when H becomes 0, B does not become 0. At the beginning, when H was 0, B was 0. Now, at the point B, H is 0, but B is not 0. That value of B is called retentivity. So resultant field retentivity may be represented by the distance OB measured in Tesla. Measured in Tesla. Now still you try to increase the current in reverse direction. You can make the H value negative to get B0. So at the point C, you can see that B is equal to 0, but there H is not equal to 0, and that value of H required to demagnetize the sample is called coercivity. So OC represents coercivity, OB represents retentivity. If OB and OC both less, then this loop area will be less, and that is for soft iron. So soft iron, this hysteresis loss is very less. This area, when you measure, you get that dimensions of energy density, energy per unit volume. That is called hysteresis loss, magnetic hysteresis loss. This loop is called hysteresis loop, and this loop area will tell you the energy lost as heat per cycle of magnetization and demagnetization of sample per unit volume. So hysteresis loss is described as the energy lost as heat per cycle of magnetization and demagnetization per unit volume of the ferromagnetic core. Okay. For ferromagnetic materials, when you draw this BH curve, that would have different areas. That's properties of different materials. Soft iron happens to have smaller area. This thickness will be very less for soft iron. That's why hysteresis loop area for soft iron is less, which is also a required condition for a temporary magnet. While designing a temporary magnet, the core should have least hysteresis loss. Hysteresis loss is less. So when you prepare a material for choosing as a core for a temporary magnet, you choose soft iron because it has least hysteresis loss. But high permeability, low retentivity, low coercivity, all that to be satisfied, but soft iron has slightly greater retentivity. We neglect that because soft iron has much smaller coercivity. Steel has retentivity slightly less than that of soft iron, but steel is preferred as a permanent magnet because steel has much larger coercivity. Okay, that's topics are very important. And here hysteresis loss is the loop area. The one with lower hysteresis loop area is chosen as a temporary magnet. For permanent magnet, that loop area doesn't matter. Okay, so loop area will give you the heat lost as called hysteresis loss per cycle of magnetization and demagnetization per unit volume. Okay, so this topic is also very important. With that, we could complete the theory of that chapter within the prescribed time, less than 1 hour. And it's a very small chapter. We'll be meeting you with the next chapter soon. Next chapter is electromagnetic induction. You will receive the video of that soon. Thank you. Thank you.